Hi everyone and welcome to the last video on trig graphs. So we're looking at the tangent graph. So just on this blank piece of paper, I know you don't have this on your packet. I just want to give you a quick little overview so when we go into the next slides, nothing will be out of the ordinary. So as of now, we've been doing these graphs. Very sloppy, but I just want to show you something really quick. Okay, so we've been doing sine, right? Sine starts at the origin, up, down, like that, and of course it continues forever and ever and ever. And then we had the cosine graph, and the cosine graph starts at a max or a min, depending on the negativity of it, and it just does the same exact thing. And you know that the sine graph and the cosine graph are the same, they're just about 90 degrees out of phase from each other. So if you moved one to the left or right 90 degrees, you wouldn't know what you were looking at. You couldn't tell if it was a sine or cos because it kind of looks the same. So today when we talk about the tangent graph, which you could easily just put in your calculator, this is what it looks like. It's actually pretty cool. Let's see. We'll go right here and here. And this is basically the shape of a tangent graph. You'll know it because it's very unique. It looks like the slippery when wet signs. Here, I have one for you. See that guy up there? Woo! Okay, so it goes like this. Comes out of the sky, crosses through the origin, goes down. Now you know this repeats, right? Just like the sine graph and the cosine graph, it's going to do the same thing again. It's going to go like this. Woohoo! And then over here, same idea. Now I might not be perfect with these drawings, but I wanted you to just see what the heck a tangent graph actually looks like. And talk about one thing. Right here, you can envision that there's this line that the tangent graph is sort of avoiding, like a magnetic line that it just won't touch, but it gets really, really close. Okay. Now we've done other graphs of other functions, so this shouldn't be brand new to you, but it does happen in tangent. These lines are called asymptotes, and it's where the graph won't touch. And we evaluate this graph. It goes up, 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 and then, oh my God, I can't touch this line, I can't touch this line, I can't touch this line. And somewhere, you know, in Willy Wonka's chocolate factory where you can't see behind the door, this thing jumps over to the other side, comes up this way, and continues its journey from left to right. So, moving from left to right, that's how we evaluate whether graphs are increasing or decreasing. You'll notice this is always increasing. Okay, so where are these values coming from? So sine over cos is what tangent is defined as. So when we make a graph, we're just plotting the fraction. It's, you know, no miracle going on. So let's take a look at some of our exact values. Now I know many of you have actually memorized tangent, which is cool, in addition to the sine and cos, so this won't be a surprise to you. But when you take 0 over 1, well, you're going to get 0. 1/2 divided by radical 3 over 2 turns out to be radical 3 over 3. And for those of you playing at home, that's kind of like this, roughly. Of course, it's a non-ending decimal, right? You get that. Okay, this one's kind of cool and important. At pi over 4, 45 degrees, don't tell anybody, it's actually 1. You know, because you could see, right? Radical 2 over 2 divided by radical 2 over 2 is 1. So that's a nice one. The next guy, pi over 3, 60, that's going to be radical 3. And in case you're wondering, that's about 1.7 with unending decimals. Now this, my friends, I don't think I can fit it. I wish I could. Hang on. ASYMPTOTE. Okay, this is where the asymptote occurs because 1 divided by 0 is undefined. And that's why you get those lines. Okay, so when is tangent 0? These are some important things to know. When would your tangent be 0? Well, looks like anywhere sine is 0, that's when your tangent would be 0. And where's that going to happen? Well, the sine is 0 at 0 degrees and every 180 degrees after that. I mean, after all, if you take a look at the unit circle quickly, these 4 coordinates here are what we're talking about. At 0 degrees, we have a coordinate of 1, 0. Up here, we have 0, 1, -1, 0, and 0, -1. Now, you recall that these coordinates on this unit circle stand for cosine and sine. So let's check out this second one to see where you 0. Well, right here and right here. So that would be 0 degrees, or 360, or 720, and so on. And this would be 180 degrees. But you know the unit circle, right? It goes round and round and round and round and round. So sine's going to be 0 infinitely amount of times at 0 degrees, 180 degrees, 360 degrees, and then another 180, and then another 180, and so on and so on. So we can kind of write that out really cool. We can say that tangent will be 0 at 0 degrees plus pi 180 times some n, and any integer. Negative or positive, it's going to work, right? So let's just write n is integer. It's just a fancy schmancy way, pinkies out, you're at the dinner party with all the math teachers, and you're talking very fancy, and you're saying, oh, I know when sine is 0, it's at 0 plus pi n. Okay, it just tells us that it goes on and on and on and on and on. So same thing for tangent equals 1, right? Tangent equals 1 anywhere that sine equals cos. And the last one, which is critical, when is tangent undefined? That happens over here when the cosine is 0. Okay, so where's cosine equal to 0? Let's go back to our unit circle. Here's cos, first coordinate, here and here. Okay, that's 90, or pi over 2. And this guy's 270, or 3 pi over 2. And that's where the zeros are going to happen. And again, it's going to go on and on and on and on. It's just going to keep going. So once you get to pi over 2, if you went another 180 degrees or another pi, you'd be back at cosine 0. And another pi, you'd be back at cosine 0. Even if you went negative, negative pi, cosine 0. So let's be fancy schmancy and call this pi over 2 plus pi n. Nice. Now if you want to pause the video, just take a second to fill out this graph, as I did. Okay, so you've labeled your graph, no different than any other graphs we've been doing, like sine and cos. But let's plot this. I mean, you know what it looks like because I gave you a heads up in the beginning, but let's see where this comes from. Okay, so looking at your chart, we'll go purple. Looking at your chart, you had at 0, the tangent was 0. That's easy. So let's say that this is 1 and this is 2. -1, -2. Okay, so in the first quadrant, 0 to pi over 2, what were our values? Well, at the first special angle, pi over 6, we had radical 3 over 3, which we said was about 0.577. So we come up here, we go to 5, halfway, right, and a little bit up. Cool. At our second key value, pi over 4, that was when it was equal to 1. At our third key value, pi over 3, we said it was equal to radical 3, which was about 1.7. So we're getting very close to here. Cool. Now, when we get to pi over 2, we said it was undefined. So let's put in a red line here, and we'll just do this. Just so we remember there's no way that this graph can touch that line. Okay, so leaning on a little bit of your trig knowledge, okay, you know this is symmetrical. So when we walk back into the fourth quadrant, into the negative angles, and you look at your unit circle, you'll notice that it's very symmetrical and the values just repeat. So when we go to negative pi over 6, it will just be negative 0.577, which will be somewhere over here. Then when we get to negative pi over 4, it's going to be 1. When we get back here to the third special angle, which is pi over 3, 60 degrees, you get negative 1.7, which is very close to 2, and it's right about here. Now we have another asymptote, which we cannot touch. We know that that happens every 180 degrees, or every pi, whether it's to the right or to the left. So we're going to do that. Okay. So let's connect this graph, make it look fluid, and you'll see it looks just like what I had graphed for you in the beginning. Cool. That's it. That's tangent. So symmetrical, right? So this continues on and on and on. So it's going to go through like that. Very cool. And it's going to come out of here like that. What's the range? Well, you can see it's going up to the sky. Down south, there's arrows. This never stops. So the range is y is greater than negative infinity, less than positive infinity. What's the domain? It's all real numbers, except those asymptotes. Okay. You know, so where are those asymptotes happening? Remember we had this really fancy way of saying it. Add pi over 2 plus any amount of pi's. Now this n can be negative, okay? So, you know, you say plus any amount of pi's. Well, it would be like saying subtract if you want to go left if this n happened to be negative, that's all. So it all works out. And when is the graph increasing? Hello, always. All right, so what about the shifts? These are critical. Take a moment to label your graph like I have, and then come back. Now, a regular tangent function goes through the origin and is mapped just like we did. Haha. However, -2. Okay, as you guessed, this is not difficult. This is -2. There's your new origin. There's your midline, right? Remember midline? So that D is like your midline. Bam, there you go. So now your origin has been sent down 2 units, and the graph has dropped. So what hasn't changed is the asymptotes. They're still here at pi over 2 and negative pi over 2. It's just that your tangent graph dropped down. Your range has not changed. So we could also draw that here, except now I'll be going through -2 right down there, and I'll be going through -2 right down here. There's my new origin, or my new midline. And here's some nice sketches. Perfect. Cool. All right, so as you can imagine, the next graph, let's go left and right. Let's go right pi over 4. Now, I did pick a tricky one. I didn't pick a shift that was equal to one of these intervals here, like pi over 2. So you might have to do some work here to figure out that pi over 4 is halfway from 0 to pi over 2. What would a shift to the right of pi over 4 look like? Well, let's take our origin and move it over pi over 4, which again is halfway to pi over 2. So what that does is it takes everything and shifts it over pi over 4. So remember we said that the asymptotes exist at pi over 2, right? Well, now we have to move them over to the right. So here are our new asymptotes. And then we said it happens every 180 degrees. So that means, wow, we have another one all the way out over here. Pi over 4 past that tick mark. Then when we work our way backwards, we have another asymptote over here. Now, what did I do with these asymptotes? I just moved them to the right, pi over 4. That's all. My little origin sucker right here, bam, you're over to the right, pi over 4. This asymptote to the right, pi over 4. That's all we're doing. Just shifting everything over. So here's my new tangent graph. Let's go purple. Check it out. I know I got to go through here. I know I'm just touching this asymptote here. Whoa, whoa, not touching, sorry. Just almost touching, approaching as they say. Cool. Now, where am I going to go through here? I usually go through pi, right? So let me go pi over 4 to the right. I'll go through here now. And this guy, I usually go through negative pi. So now I'm going to go pi over 4 to the right. And let's connect. Very cool. You just did a shift on tangent. Not bad. Not bad at all. Cool. So listen, something very important, because I see it right now. I hope you didn't already pause this video or fast forward. For those of you who are still with me, this is a bonus for you. Thanks for staying around. You might be thinking, remember our last graph was down 2? So you might be thinking, hey, how do I know if someone flashes me this picture and says, hey, what did I do to this tangent graph? How are you going to know that it just wasn't shifted down 2? Or I don't know, maybe in this case 3, because there's 3 boxes. But how do you know? That could be tricky. I'll be honest with you, that could be tricky. So your key indication about whether or not this was a tangent graph that got shifted down like our last one, or has been shifted right or left, will be the asymptotes. That's the key. That's how you can tell. Because, I'll be honest with you, this certainly looks like, oh, I know tangent, that's a slippery when wet sign, that's easy. And oh, check it out, it didn't pass through the origin, it passed through down here. Someone must have just gave it a new midline, or a D transformation. But upon careful inspection, if you notice where the asymptotes are, you might say, wait a minute, the asymptotes are usually at pi over 2 and then every 180 degrees left or right. It's a little bit to the right of pi over 2. Well, then that would explain how this guy dropped, Okay, anyway, I've said too much. So let's do the last one, which is negative. So I just wanted to show you negative because here at a negative graph, this is always decreasing actually. And check it out. It still has the same range and domain and all that jazz, but it is certainly, oops, hang on. Okay. It is certainly always decreasing, so watch. Green. Still have the same origin. Still have the same asymptotes. It just reverses. Sweet. Woohoo! Okay, that's the negative. It just reflects over the x-axis. Put it in your calculator. Put both of them in your calculator. It looks kind of cool, like an hourglass. You know, put the positive and the negative. It's really kind of neat. All right, so as you can see, if you walk from left to right, you'd always be walking downhill, and then of course falling into oblivion. But then you'd magically hop over, and you'd be falling down again and falling down again. So negative tangent has all the same properties as tangent. It's just that it's always a decreasing graph. So anyway, that was a nice introduction to tangent for you, and I hope you enjoyed the video. We'll see you tomorrow. Have a great night.